In this section, we're going to take a bit of a deeper dive into some of the things that I've kind of glossed over in the last couple of sections. So, especially expressions, which are a bit complicated, but also kind of one of the main things about the tactic and metaprogramming framework of Lean. So, there are 5 things that we're going to talk about in this section. Well, I guess 4. Because tactic, you've already seen this, right? This is the monad where you can manage the proof state and so on and so forth. Okay, this is old news. We're going to talk briefly about names. So a name, well, is the name of a definition or a lemma or something. So for example, x or even.add2. We're going to talk in detail about expressions, because these represent the actual Lean programs or terms or expressions that we generate. So these are quite interesting and useful for tactic programming. We're going to talk about declarations. So a declaration is all the information that Lean has about a definition or a lemma or a theorem, including its type and its body. So the actual thing being defined. And we're going to talk very briefly about environments. So an environment is essentially a list of all the things that Lean currently knows about. So all the declarations, all the notations, all the lemmas, all the theorems, everything. Okay, let's go to names first, because these are actually quite simple. So here we can print the type name, and you can see here unfortunately in a slightly smaller font. I didn't really find a way to make the font bigger here, so sorry about that. But what you can hopefully decipher is that this inductive type name has a couple of constructors, so you can have an anonymous name, and then you can have a name with a string component attached, and then you can have a name with a numeral component attached. So these numerals are not really useful for us. So the main takeaway is a name is just a list of strings. And so, for example, the name even.add2 is composed of the strings even and add2. That's really all there is to a name. Next up, we're gonna talk about the expression type, which unfortunately is much less simple than the name type, and I'm gonna walk you through some of that complexity. You're not expected to remember all of this kind of on the first hearing. This is going to reappear in the exercises, and then you'll probably want to look up the chapter of the Hitchhiker's Guide and refresh your memory. Yeah, I'll tell you about it so that you've heard about it at least once. So, expressions, or the expression type, which you can see here is an inductive type with a lot of constructors. Its purpose is to represent Lean expressions. So essentially every Lean program that you can write has to be represented as an expression. And to do that, Expr is what we call an abstract syntax tree. So essentially for each construct of the Lean language, so for example lambdas or variables or pi types or let bindings, for each of these things we have a constructor of the Expr data type. And essentially I'm going to walk you through each of these constructors and tell you what they do. So let's start by setting up a simple example. So a function foo, and this function is gonna take a function and some x, and it's gonna apply the f to the x. Okay, simple enough. So this whole thing here is a Lean expression, or a Lean program, if you will. And so there is an inhabitant of the Expr data type which corresponds to this expression. And we're gonna build that kind of step by step. So first of all, let's talk about the app constructor, which for some reason isn't listed here, but I'll just add it real quick. So app, as you can see here, is a constructor of the expr data type, and it takes two expressions and gives us an expression back. And this represents function application. Right? So if we imagine that f and x are also expressions, then expr.appfx stands for the application of f to x, i.e. exactly this thing here. Yeah, there's not really much more to the expr. Oh yeah, you have to remember though that if you have something like fxy, then application associates to the left. So this is the same thing as f applied to x, and then this whole thing applied to y, rather than the other way around. Yeah, that's really the only subtlety related to the app constructor. Okay, let's delete all that so that we don't have these errors in here. Okay, next constructor that we're going to talk about is lambdas. And these represent, well, lambdas, like this one for example. And essentially the expr constructor contains all the information that we have about something like this lambda here. So it contains a pp name. So this is the name of the variable that we are binding. So in this example that would be f. It contains a binder info. This indicates whether the lambda is explicit or implicit or an instance argument or one other possibility that we don't talk about in the course. So usually this will be binder info.default, which means it's an explicit argument. And then here we have the type of the bound variable. In this case, this would be n to n, and this type is also an expression, right? Because in a dependently typed language, types are, you know, programs like everything else, conceptually at least. And so this is just another expression. And then the last component of the lam constructor is the body of the lambda, right? So this is essentially the part after the comma, so this entire thing here, if we're talking about the first lambda. And so this is another expression. Now let's try to put this into practice and represent this whole thing here as a lambda expression. So we're gonna define the foo expr, and this needs to be a meta definition because exprs live at the meta level, and so everything that involves an expression also needs to be at the meta level. So the first thing that appears in this expression is a lambda. So we're gonna start with the lam constructor, and the name of the variable that is being bound here is f. This is an explicit lambda, so we take binder info.default. The type of this lambda is n to n. Now, what is this notation with the apostrophe and the parents here? I'm gonna get to that in a bit, but essentially it's just a convenient way to construct expressions. So this here is the expression corresponding to this thing. Anyway, more on that later. Okay, now the last thing that we need to fill in is the body of the lambda. So this is this expression here, and it starts with the lambda again. So this one names its variable x. It's again explicit. The type of it is n. And now we need to have the body. And the body is an application, right? It is f applied to x. Okay, and now the question is, what is the representation of f and what is the representation of x? And for that, we need to look at one more constructor of the expr data type, namely this var constructor, which is used to represent variables. And the way we represent variables is a bit inconvenient, but it is like very convenient on the implementation side. Yeah, but you have to kind of get used to it. I'll explain the general principle. So we represent variables as what is called de Bruijn indices, and I hope I didn't butcher that name too hard. Now that I'm in the Netherlands, I always have to take care not to butcher these names too hard. Yeah, but a de Bruijn index essentially represents a variable by saying how many lambda binders do we have to jump over to find the binder that binds this variable. So here, for example, the x is represented by the variable 0 because we have to jump over 0 lambda binders to find the lambda binder that binds x. Right? So if there were any other lambda binders between the x and its binder, then we'd get higher variables. For example, for the f here, this is the variable 1 because we have to jump over one lambda binder, the x binder here, in order to get to the lambda binder that binds f. So yeah, something that you have to get used to, but you'll probably get used to it relatively quickly. It's not like the most advanced concept in the world. So here, the f is going to be variable 1, and the x is going to be variable 0. Okay, now I think I've completely broken Lean, but we can restart it, and then hopefully it's going to get its act together, and it did. Okay. So, this is how we represent lambda terms, and this is kind of the most difficult part of representing expressions, so the rest of the constructors will be a little easier. Yeah, let's just go in order now. So, expr.const represents a constant, and a constant is basically anything that you can define. So, inductive types are constants, definitions are constants, theorems and lemmas are constants, everything that you define is a constant. And you refer to these constants by name, so when you represent them as an expression, you just give the name here. And so, for example, this is the representation of the type n. And here's a list of universe parameters. Don't need to worry about these. I don't think they're going to come up anywhere in our examples in any case. Alright, next thing, the sorts. So these are the universes that Lean has. I'm not sure in what detail you've talked about these, probably not in much detail, but I'm just going to tell you a bit opaquely that Lean has an infinite hierarchy of universes called sort 0, sort 1, sort 2, sort 3, etc. And some of these have kind of commonly used names. So sort 0 is usually called prop, sort 1 is usually called type, sort 2 is usually called type 1, etc. Yeah, and the way you represent them is by just saying, okay, it's a sort, and you give the universe level, which is a natural number, essentially. So it has a 0 constructor and a subconstructor. And yeah, that's how you represent universes. Okay, the Var constructor, we've already done that. Local const is used to refer to a hypothesis, and if you've paid a lot of attention, we've actually seen one of these local const things in the previous sections. So yeah, this refers to a hypothesis in the context, and these hypotheses always have a unique name, which is an internal name that you don't usually get to see, and that is automatically generated by Lean. Okay, here we are, sorry about that. Then we have a PP name, which is a pretty name. So that is the name that you actually see in the context. Then we have again a binder info, which indicates whether the hypothesis was an explicit or implicit argument. You can mostly ignore that. And each of these hypotheses has a type. Now, unfortunately, Lean sometimes lies about these types, so these are not always reliable, but I don't think this comes up in any of the examples. Okay, next thing is a meta variable. I don't think you really need this. So these are the question mark thingies that sometimes appear in goals. They have a unique name, they have a pretty name, and they have a type. Again, don't think you need to know anything about this. So a pi is one of the more interesting constructors. So this is very similar to a lambda constructor. In fact, you can see here that it has exactly the same structure. It also has a pp name, a binder info, a type, and a body. And this is used to represent pi binders. So let's say we define a type here, and that type is gonna be for all x n, x greater than 0. Okay, that's the type. Then this for all here is called a pi binder. And we call it a pi binder because we can also write it as pi. Yeah, these work exactly as lambda binders, right? So again, we have the name of the variable, the type of the variable, and the body of the pi binder. And so, yeah, you can use that pretty much just like you use the lambda above here. One thing that we should note, we can define another type, and this is going to be the type n to n. So behind the scenes, this is the same thing as pi something of type n, comma n. So it's just a pi binder where the bound thing doesn't appear in the body of the binder. Right, and the syntactic sugar for this is the arrow. So when you have an arrow type like this, and you want to represent it as an expression, you'll actually need to use a pi binder. Okay, and then we've already talked about the lambdas, and then the last two, I don't think these ever come up in the course. So these are let definitions, and these are macros. Yeah, no need to worry about those. Okay, so now that you know what an expression is, we can go back to something that I kind of jumped over earlier, which is the difference between elaborated and unelaborated expressions. So let's maybe start with unelaborated expressions, which are also called pre-expressions. So these are essentially the things that you write in the surface language of Lean. So like just your programs as you write them, and these then get translated into what is usually called a pre-expression. And the thing about these pre-expressions is that they can omit a lot of information that you don't have to write explicitly. In particular, you don't have to write implicit arguments, and you don't have to write instance arguments, because Lean figures these out for you. And this Lean figuring it out for you is done in a process called elaboration, which takes an unelaborated or pre-expression and turns it into an elaborated expression. And the difference between the two is just that the elaborated expression contains all this information that you previously left implicit. So it's the same thing, but with all the implicit arguments and all the instance arguments and everything filled in. Right, and we also, like, whether an expression is elaborated or not is indicated by this parameter here. FF stands for not elaborated, and TT stands for elaborated. And we, like, elaborated expressions are usually more useful for metaprogramming, and this is why we can also say just expr, and this is the same thing as expr TT. So we can leave the TT implicit there. Right. So this is gonna be interesting when we talk about quotations in the next section right here. So in the previous like just a few minutes before, I told you how to construct an expression for like something that you might write in lean surface syntax, and you maybe thought, okay, this is super annoying. I don't really want to do this explicitly, and you wouldn't be alone. And this is why lean has a convenient quotation mechanism which allows you to essentially give expressions, so inhabitants of the expression data type, with a much more convenient syntax. And so what you do essentially is you write backtick parentheses, and then within the parentheses you write the thing that you would usually write in when you're writing lean. And then what lean does is it translates this thing into the expert data type. So if we look at the output of tracing E here, then, well, okay, the trace is exactly what we wrote here. And if we trace E.toRaw format, then we can see, all these constructors of the expert data type that lean has constructed for us. And as you can see, this gets out of hand pretty quickly. And so it's very nice not having to do that explicitly. So, yeah. So, the thing about these single backtick quotations, so this whole thing is called a quotation. And the thing about these single backtick quotations is that they only construct elaborated expressions, which means that lean must be able to figure out all the implicit arguments and instance arguments and everything that occur in this expression between the parentheses. It has to be able to infer these at compile time. And if it can't do that, it's going to fail. So, for example, in this example, we leave a hole here, and where previously we had this function, and lean doesn't know how to fill in this function because it's an arbitrary function. How is lean gonna know? And so it fails because it can't fully elaborate the expression between the parentheses here. However, we can also construct pre-expressions with a slightly different syntax, where we have the double backticks here. And the difference is that in pre-expressions, obviously, well, we can leave holes, and lean is going to be perfectly happy with that, because it's just going to translate this expression pretty much verbatim into the expression data type without doing much of any interest. So if we look at the output here, we see that the first expression is some sort of map, and well, we have some garbage here, frozen name and whatnot. This is not something you should be worrying about. And yeah, then in the second example, so this is this expression, we see that lean has inserted a hole here. So and if we want to do much of anything with this expression, we're gonna have to replace this hole in some way, and we can do that with all kinds of tactics, but that's not something that we're gonna worry about right now. Okay, and then there is a last sort of quotation that I don't think is gonna come up often, but it is occasionally useful. So here we use 3 backticks, and these also construct pre-expressions like the double backtick ones, but they don't even check that the names that we use here are correct. So here Seattle.Washington obviously is an inexistent name, but it's gonna accept that anyway, and it's gonna give us back the exact expression that we wrote here without any name checking whatsoever. In fact, let's talk a bit more about names while we're at it. So I've kind of used these previously without really introducing them. But when you want to write a name, you don't usually write the constructors of the name inductive type that I showed earlier. Rather, you write backtick and then the the actual name that you need. Note there's a big difference between backtick and just the name and backtick parenthesis and the name, because with the parenthesis you are constructing an expression, and without the parenthesis you are constructing a name, which are of course conceptually completely different things. So need to keep that in mind. Okay, now here we have a couple of names, and again we have kind of a slight variation. So with a single backtick here, it just constructs the name, and it doesn't check that this name exists or anything. It just, it gives you a name object and nothing else. When you do two backticks, then it actually checks that the name in fact exists. So here, for example, when we do the Seattle, Washington name, which doesn't exist, then it gives us a failure, which is what we want in most situations. So, like, usually you actually want to use double backticks instead of single backticks. Next thing we want to talk about is anti-quotations. So you've just seen quotations. Now we're going to do the opposite of quotations in some sense. And an anti-quotation, well, it's essentially something that allows you to embed an existing expression into a bigger expression. So for example, here we construct an expression 2 of type natural number. We have to give the type annotation here because otherwise Lean doesn't really know what this 2 refers to, right? It could be a real number, it could be a natural number, it could be a rational number, any of these things. And now here, down here, we can insert this x into a bigger expression, and we do this by essentially writing a quotation here containing this +1, and then we refer to the x with two percent signs. And this essentially says, okay, this x is the x that we defined up here, and Lean essentially then just inserts this 2:n down here, right? So this is the same thing as this guy, right? And this is what anti-quotations do, and you can see here, okay, the result is 2 + 1 as expected. Yeah, you can do this with normal quotations, you can do it with double backtick quotations, you can do it with triple backtick quotations. This all kind of works as expected. And here's another very interesting feature of anti-quotations, which is that you can use them in patterns. So when you want to deconstruct an expression, you usually want to say, okay, the expression is expected to have a certain form, and then some parts of the expression you don't know what they're going to look like, and you want to analyze them further. And this is what you do with a pattern match like this. So essentially, the pattern match here says, okay, the target, which you get by calling tactic.target, the target is expected to have the form a plus b equals c for some a, b, and c. And we can look at the output here. So if we trace a, b, and c, then we see that a is 1, b is 2, c is 3, because we had a lemma of this form as the target. And you can also you can also do this with the add notation. So if you wanna also bind the type of things that are being equated here, you can do this more verbose at EQ notation, and then it's gonna bind the alpha and the left-hand side and the right-hand side of the notation. So this is because when we hover over this here, we see that EQ is actually takes 3 arguments: the type of things that are going to be equated, and then the 2 things that are equated. And if we want to know what the type is as well, then we have to use this add EQ notation, and then we can bind even the implicit arguments of EQ. That's essentially what the add means. It means make every implicit argument explicit. And so we can use that in order to bind the alpha and the left-hand side and the right-hand side. And so let's look at that. So the alpha is n, because both the left-hand side and the right-hand side are natural numbers. And then the left-hand side is 1 plus 2, because that's what we have here. And the right-hand side is 3, because that's what we have here. Now to finish up this section real quick, something about the declaration type and the environment type. So you can see the declaration type here. Essentially you can just get all of the information about a declaration out of this declaration type, and a declaration is pretty much anything that you can define in a lean file, right? So you can see here that there is a constructor for definitions, there's a constructor for theorems, there's a constructor for constants and for axioms. And so whenever you define something like this in a lean file, you can later on get the declaration, and then you can find out, you know, what's the type of the definition, what's the body of the definition, all these kinds of things. And then the environment type. So the environment is essentially a list of all the stuff that is defined so far, like all the inductive types, all the definitions, and so on and so forth. And if you need to query all the environments, which we're actually going to do later on, so this is why we mentioned here, if you need to query all the definitions, then you can use this environment.fold function. And so essentially this iterates through the environment and allows us to do something with every declaration that is present at the moment. And so here, for example, this is a fold that just takes the number of declarations that are currently known to lean. So it starts with 0, and then for every declaration we add 1. And yeah, if we run that, then we see that there are 41,000 declarations currently known to lean. I expected it to be a lot, but I didn't expect it to be that much. So yeah, lean has a lot of declarations.